looking at acids and bases, we know that acids are going to have a pH range between 0 and 6. So anything on the pH scale that's below 7 is considered an acid. The closer it is to 0, the stronger the acid is. The closer it is to 6, the weaker the acid is. So if you kind of think about 7, we know is neutral. So the closer you are to neutral, the weaker it's going to be, because the more like water you would be. The further you are from neutral, then the stronger it's going to be. And whenever we have acids, they're going to break apart and they give off a hydrogen, which we also call a proton. So that H plus right here is what's given off in an acid. And what this H plus does is it joins with water and we form what's known as the hydronium ion. So you can see an acid written just like this, the H plus, or also like this, H3O plus. And with formatting, really the plus would be up on the top as a superscript, but it doesn't show up like that on here, but that's okay. So you'll either hear it called a proton, which would refer to this, or hydronium ion, which would refer to this. Typically in class, we're going to be calling it hydronium ion, and we will be writing it as a H3O plus. And then the leftover is going to be a negative ion because the positive is gone. So it's not only the hydrogen, it's also a positive charge that's broken off from the acid. So if we look at some examples, we add acid to water. So here's our water, and this is hydrochloric acid. We use this quite often. And so you have the H right here, and it's with the chlorine. But what happens is this H is given off and goes with the water and forms our hydronium ion. So here's the hydronium ion. And then here's the leftover, which is the chlorine ion. And so the leftover here is a negative charge. Once again, this would be a superscript, but because of formatting, it's not. Looking at another example of an acid, nitric acid. So nitric acid, once again, we have the H right here, and that H is going to be given off and combines with the water molecule, forming the hydronium ion. Then whatever's left over has that negative charge on there. So originally the H was with the nitrate, now it's with the water, forming a hydronium ion. Another example, we've got sulfuric acid. So sulfuric acid has 2 hydrogens, but just one of them is going to leave. So one hydrogen is given off, and we form H3O plus, and then we form hydrogen sulfate ion, which is negatively charged. So every single one of these acids has done the exact same thing. They've all given away their hydrogen to the water, forming the hydronium, and then whatever's left over has a negative charge on it. So looking at a picture here, here would be our water molecule, here is the acid, and then here would be a picture of our hydronium ion. So now we have the addition of the hydrogen, and that has a positive charge. And then as you can see, the hydrogen is gone over on this side over here, and we've formed the negative ion, the leftovers. So the hydrogen just basically moves from here to there. And that's all that acids do. So acids are going to have a pH level below 7. And they are going to contain hydrogen. That's the easiest way to pick them out. And if you noticed that all of the hydrogens were written right at the beginning, like HCl, H2SO4, HNO3. And the ion formed in an acidic solution is called the hydronium ion. So we form hydronium ions. That's H3O plus. So when we look at bases, bases have a pH range between 8 and 14 because we said 7 is neutral. And once again, the closer it is to neutral, the weaker it's going to be. The further it is from neutral, the stronger it's going to be. So a pH of 8 is really close to 7, so that's going to be weak. A pH of 14 is far away from 7, so that's going to be strong. And then bases give off what's known as the hydroxide ion, which is an OH minus. So when we compared the two, we said acids give off a hydrogen, which forms the hydronium ion. Bases give off the hydroxide ion. So looking at some examples, we've got sodium hydroxide. So as you can see, here's the OH right here, and it's forming our hydroxide ion. Then we have calcium hydroxide that has 2 OHs in there, and so it's going to form a hydroxide ion on there. So bases are going to contain hydrogen and oxygen. Then you have bases have a pH level above 7, and the ion formed is called the hydroxide ion. So we know that pH affects how, or tells us if an acid or base is strong or weak. So we said the closer it is to 7, the weaker the acid or base is going to be. The further it is from 7, the stronger that acid or base is going to be. But what makes it have a pH of 7? What makes it have a pH of 14? What makes it have a pH of 3? So if we're talking about the strength of it, it's all about how many ions are formed. We said acids form hydronium ions. So when we have a strong acid, that means we're going to have a lot of hydronium ions. So that means that HCl or that HNO3 or any of our examples of acids, all those H's are going to leave the chlorine, leave the nitrate, leave the sulfate, and form H3O+. So we're going to have a lot of ions in there. The only way we can form these ions is if that acid breaks apart and gives off that hydrogen, because that's what acids do. They break apart and give off the hydrogen. So that's the only way that we can form our hydronium ions. The more hydronium ions there are, then the stronger the acid is going to be. Now, when we're looking at bases, bases revolve around hydroxide. So hydroxide ions, the more hydroxide ions we have, the stronger the base is going to be. So in order to form those hydroxide ions, the hydroxide has to break apart from whatever it's combined with. So for sodium hydroxide, you would have to have the sodium and the hydroxide separate and break apart. Calcium hydroxide, the calcium and the hydroxide would have to separate and break apart if it's a strong acid or a strong base. So you have to have them all pretty much breaking apart. And then your pHs are going to be really low if it's an acid or really high if it's a base. Now, what about a weak acid or base? So when we have a weak acid or base, the pH is closer to 7, and when we add it to water, only some of the acid or base molecules are going to break apart. So we're not going to have as many hydronium ions in our solution if it's an acid. Or if it's a base, we're not going to have as many hydroxide ions in our solution. So it just depends on if it's an acid or base. So acid's hydronium, base is hydroxide. The more ions you have, the stronger it's going to be. The less ions you have, the weaker it's going to be. And you can kind of think of it, if you have a strong acid or base, remember, then they're going to be separating. They're more independent if they're strong. So they like to be by themselves. So they like to separate from the acid, or they like to separate from the base. If they're weak, they always have to be attached to something. So they are not independent. They're not strong enough to be by themselves. So therefore, they like to stay with whatever they're combined with. So magnesium hydroxide. So the hydroxide likes to stay with the magnesium because it's too weak to break apart and be independent, be on its own. So the more breaking apart we have, the stronger it is. The less breaking apart we have, the weaker it's going to be. So when we combine an acid and base together, we know that acids give off hydrogen and bases give off hydroxide. So what we can do is we can actually add those two things together, and we're going to form water, and then the leftovers from the acid and the leftovers from the base form what is known as a salt. And we know salts come in many forms. And when we do that, of course, we're going to form water, which is neutral. So we're going to have a neutralized reaction, and we know the pH is around 7. So if we look at a acid-base reaction, so we have our acid. We know this is the acid because we have the hydrogen, HCl, because we can identify a lot of acids with that hydrogen in the beginning. And then we have sodium hydroxide. So we identify the hydroxide in the base. So HCl is our acid, NaOH is the base. And what's going to happen is the acid gives away the hydrogen, the base gives away the hydroxide, you have an H and you have an OH. And so that's what's going to form your water. Then we have the leftovers. So you have the chlorine and you have the sodium. And so that's going to combine together to form sodium chloride. Remember, the cation always has to go first. Sodium is a cation, it's Na+. Cl is an anion, it's Cl-. So when they combine together, it'd be NaCl. If we look at another example, same thing happens. So this is nitric acid. So we identify the hydrogen right at the beginning, which indicates to us that this is an acid. We have the hydroxide at the end, which indicates that this one is the base. So we have the H given off from the acid, the OH given off from the base. HOH makes water. So we have our water that forms right there. And then the leftovers. So we've got some nitrate left over, and we've got some calcium left over. And so those will combine together to form calcium nitrate, which is another type of salt. And so these would have a pH of 7. That's why if you ever in the lab spilled an acid or spilled a base, we would want to add the opposite to it to neutralize it and then clean it up because it'd be much safer to work with. So if we have a lot of hydroxide ions, so hydroxide indicates a base, and if there are a lot of ions in there, that means they all kind of broke apart, so they're independent, which means they're strong. So this would be a strong base. Then if there are a few hydronium ions, so hydronium ions refer to an acid, and if there's only a few of them, then we know it's not very strong, it's not very independent, so therefore that's going to be a weak acid. And when we have an acid and base together, we know that the acid is going to give off the hydrogen, and the base is going to give off the hydroxide, and that's what forms the water, and then the leftovers always form our salt. Everything that's part of a neutralization reaction, water and salt are the products, acid and base are the reactants. And a strong acid and a strong base are independent. That means they're going to break apart. If we want to look at how to draw and show a solution that is strong or dilute or concentrated or weak, what we can do is we can just use an example of a strong and a weak acid. So in the first box, what it says depict a concentrated strong acid solution. So we know a strong acid means that there's going to be a lot of ions in there, hydronium ions, and strong acids like to break apart because they're more independent of each other. So our strong acid is just HS, and so this is strong, and then it's got to be concentrated, which means that there are just a lot of molecules. So we have a lot of solute in there. So if it's strong and concentrated, we're going to have a lot of hydronium ions, which you can write as H+, or if you prefer H3O+, either one is perfectly acceptable. And then the rest of the acid is going to have a negative charge. So however you'd like to write the hydronium ion, either one is perfectly acceptable. For every hydronium ion or hydrogen you show, make sure you do have the S-. So the S- represents the rest of the acid, so it could be HCl. So this would be the H, this would be the Cl-. It could be HNO3, so this S would represent the NO3. So it doesn't matter what the rest of the acid is, but we do know that it's broken apart because it is strong. So this is going to be an S- and another H+, and there's a lot of them in here because it is concentrated. So now if we look at box 2, we want a dilute strong acid. So it's still strong, which means it's going to all be broken apart because it's independent, but now it's dilute. So dilute just means that we don't have as much solute. And of course, water is our solvent in all of our acid-base reactions here. So if water is the solvent, then the acid would be the solute. And so we're just going to have a couple of these. And once again, it doesn't matter if it's H3O or H+. So these pictures are very similar in which we show that all of the acid is broken apart. The difference is the amount. So concentrated, we'd have a lot of them. Dilute, we would not have that many. Now in the third box, we want a concentrated weak acid. So HW represents a weak acid. and this is once again going to be concentrated. So in a weak acid, remember, they're not that independent. They're pretty weak, so they like to stay together. So therefore, we'd have a lot of HWs together. However, they're not all together, because if all of them are together, then it is not an acid. So we do have to break some of them apart. And we can continue to add more in here because this is a very concentrated solution. But the difference between this one and the one above it is that now we see we have some of these are connected to each other. They're not strong enough to break apart. So that's what makes this a weaker acid versus this one here, they're all broken apart. So that's a stronger acid. And in number 4, then we have the dilute weak acid. So once again, weak meaning that it's staying together, but not all of them stay together. Something has to separate out because we have to still have that ion in there to show that this is an acid. No ion means no acid. So we still have to have that ion in there, but now we can see that there's very little of it. And so this would be a weak dilute acid. So the difference between concentrated and dilute is simply the amount of molecules I put in here. The difference between strong and weak is simply how many are broken apart and how many are together.
So another aspect of acids and base are going to be conjugate acids and base. And conjugate acids and bases always come in pairs. So typically when we think of a base, we think of a base as having the hydroxide ion in it, but we were able to find substances that didn't directly contain hydroxide that had a pH level above 7. So we had to kind of expand our definition of a base. So a different type of base is one that also accepts an H+. So we know an acid gives off that proton, gives off that H+. So then the opposite would be a substance that takes in the H+. And then after it would take in an H+, it would form what's known as a conjugate acid. So conjugate acids or conjugate bases are always on the product side. Always, always, always products. So if we look at an example, we've got ClO minus, and then this is going to be plus H2O. And then there's going to be an arrow right here. It's an invisible arrow right there. And so these would be our two reactants, and then these are the two products. So it forms HClO plus OH minus. So as you can see, we've still got some hydroxide ions formed in here, but it's in an indirect way. So when we look at this substance right here, you're like, well, that doesn't have hydroxide, which is what we normally would use to identify a base. In this case, we're forming hydroxide ions in a little bit different way, which is increasing the pH. So in this case, it's going to take a hydrogen from water, which technically makes water, in this case, an acid, because it's giving away a hydrogen, and that's what acids do. They give away a hydrogen. So as you can see, we have H2O, and now we have OH minus. So over here, we're missing a hydrogen. So therefore, it left. Where did it go? Well, this was ClO minus, and now it's HClO. So this is the substance that gained a hydrogen, accepted a hydrogen, which makes it a base. So this is acting as a base because it's taking a hydrogen. This is acting as an acid because it's giving away a hydrogen. And the products, so remember there's an invisible arrow right here, the products formed our conjugate acid here, which was a base, and a conjugate base here, which was an acid. So looking at conjugate base pairs, because an acid will always have a conjugate base, and a base will always have a conjugate acid. That's why we say they come in pairs. That's why there are pictures of pairs on the first screen. So if we have water here, and we look at it right here, and then we look at it over here, we can see that water got rid of a hydrogen, because here's H2O, here's just OH. So if it got rid of a hydrogen, that means that it's acting as an acid. Then we have NH3, and this is acting as a base because it's going from NH3 to NH4, so it's accepting a hydrogen. So bases can also accept a hydrogen, and as you can see through that process, we're forming hydroxide ions, which are going to increase the pH. So this is our acid, that's the conjugate base over here, and this is our base, and this is our conjugate acid. How do you decide which one is the acid and which one is the base? Well, remember, it's always going to be on the reactant side. The conjugates are always on the product side. And so to figure out which one is the acid and which one is the base, what you need to do is you need to see, did it give away the hydrogen or did it take the hydrogen? Since this went from 2 hydrogens to 1, we know that that one gave it away. Since this went from 3 hydrogens to 4, we know that one took it. So that's how we identify the acid and then the base. And then on the product side are always the conjugates. No, always the opposite. Because as you can see, the base has a conjugate acid and the acid has a conjugate base. An example of another conjugate acid-base pair. So if we look at this one, we have HNO2 plus water. And so we can see that now on the product side, it just formed NO2, which means that this HNO2 thing that gave away hydrogen, which classifies that as an acid. This water accepted hydrogen because it went from H2O to there's going to be a 3 right here, H3O. So it took in a hydrogen, and so therefore that's going to be considered a base. So then if this is the base, then that would be the conjugate acid, and if this is an acid, then that's the conjugate base. Looking at another example, we have HPO4 2 minus, and so we're like, okay, is this an acid or base? So what we have to do is we have to see what happened to it. So if we look on the other side, it formed H2PO4. So we gained a hydrogen. So if it took a hydrogen, that means it's going to be a base. And if we look at NH4, it turned into NH3. So it gave away a hydrogen. And so therefore it's going to be an acid because acids give away. When we look at the product side, if this was a base, that means this one is the conjugate acid, and if this is the acid, then this is the conjugate base. So looking at kind of a good visual of this, we can see we have the purple and the white, and we have the 2 whites with the red. So now we look over here, we can see that this white has been transferred to the red. So this gave away the hydrogen, so therefore this makes this the acid. This took the hydrogen, as you can see, no hydrogen here, hydrogen here. So that took the hydrogen, so that means this is a base. And then this would be the conjugate acid, and then this would be the conjugate base. So if it's, because there's an acid over here, it's got the base over on the other side. So thinking about this, you're like, wait, we talked about water being neutral. We always know water is neutral. Well, water can act as an acid or it can act as a base, and we call that amphoteric. So amphoteric substances can do both. So it can either give away a hydrogen or it can take a hydrogen, also known as a proton, And amphoteric substances must have a hydrogen to be amphoteric. If it doesn't have a hydrogen, it is not amphoteric, because in order for you to have an acid, it has to give away a hydrogen. If there is no hydrogen to give away, then it can't be an acid. So you have to have a hydrogen in order for it to be amphoteric. So as you can see right here in the first one, can we figure out if that's is water acting as an acid or base? So pause it for a second, see if you can figure it out. Okay, welcome back. So looking at the first example, water. So water, in this case, goes from having only 2 hydrogens to having 3 hydrogens. So we know that water is accepting a hydrogen, so it's taking it, so that is considered a base in that case. And then on this side, that would be the conjugate acid. This one is considered the acid because, as you can see, the hydrogen is right here, and now it's gone. So that means that it gave away its hydrogen, and so therefore that would be the acid, and then this would be the conjugate base. At the other example, what is water in this example? Stop, pause, see if you can figure it out. Okay, welcome back. So we look and see what happened to the hydrogen. Did it lose a hydrogen or did it gain a hydrogen? So in this case, we can see that the water lost a hydrogen or gave it away. So therefore, that makes water in this case acting as an acid. And so this substance right here is acting as a base because it goes from NH3 to NH4. So it's taking a hydrogen. So therefore, that's considered the base. So if this is the base, over here is the conjugate acid. This is the acid, and this is the conjugate base. Which of these would be amphoteric? So we said anything that has to, in order for it to be amphoteric, it has to have a hydrogen. So this would be fine. This would not work. There's no hydrogen. This would be fine. Obviously, water, that was our last example. And that does not have a hydrogen, so that would not work. Then, which of these would be considered a base? Well, we know this has hydroxide, so that works. This is an acid, it's hydrochloric acid. We use it all the time. We know that? No, because this is also going to give away the hydrogen. This one could take a hydrogen, because remember, acids give off an H plus and opposites attract, and so this is a minus. So this would love to take an H plus because it's got that minus charge on there. Positive, negative, they're going to want to combine together. The same is true for this one. Because this has a minus charge, it's going to want to act like a base and take an H plus. Plus, minus, they're going to attract. Then what would be the conjugate base of HCl? So if we're looking for a conjugate base, that means that HCl is an acid, which we know we already established. HCl is an acid, it's hydrochloric acid. We know acids give away their hydrogens. So that means that the leftover, the Cl, is going to be the conjugate base. And we know that it's going to be Cl minus because it gives away an H plus. HCl is neutral. If you get rid of a negative, you're going to be left, or if you get rid of a positive, you're going to be left with a negative.
So I want to go through a couple of the problems on this conjugate acids and bases worksheet. Some of these are just vocab words or things that you can just look up in your notes, but others of them are writing out equations, and I want to just review some of those. So in number 3, it says using labeled pictures show how hydrogen fluoride ionizes or breaks up into water. And if we see HF, so that would tell me that this is an acid. So I have my hydrogen and my fluorine, and we are going to add this to water. And we know that this is going to, because hydrogen fluoride is an acid, it's going to give away its hydrogen to the water, and the water will take it in. So we'll have now H3O plus, then now the fluorine will be by itself. And HF acted as the acid because it gave away its hydrogen, and water acted as the base because it accepted the hydrogen. So now over here, the water was a base, so now this is considered the conjugate acid. It's always the opposite on the product side. And now, because the HF was the acid, the leftovers of this is going to be the conjugate base. It's always the opposite as it was over on this side. So every acid has a conjugate base, every base has a conjugate acid. Then looking at number 5, showing how sodium hydroxide ionizes or breaks apart. So we hear the hydroxide in there, which tells us this is the base. So our NaOH simply breaks up into sodium, which is a cation, and then hydroxide has a negative charge on it. when we run a right out the reaction to show carbonate ions, so carbonate is CO3 and it's got a 2- charge, and it's going to be a weak base in water. So we're going to add that to some water. So if it's going to be a base, so then bases are going to accept a hydrogen. So this is going to be a base, which means that this is going to be an acid. And so if it accepts a hydrogen, it's going to become HCO3, and now it's just a 1- because remember it always takes an H+, so that plus is going to cancel one of those negatives on here. And then this now lost an H+, so this is going to be an OH-. So if we look at this, so if this was the base, this is going to be the conjugate acid. And if this is the acid, then that makes this one the conjugate base. Another one that we're going to have is HCl to H2O. So it's very similar to our HF one. So we have H and Cl, and we're adding this to water. And so once again, this is going to be the acid, and water is going to act as a base. And therefore, we're going to form H3O+, because water is going to be accepting the hydrogen, and so that's a conjugate acid. And then we're also going to be having the leftovers, which is just Cl-, so that's going to be the conjugate base. If we want to look at ammonia, how ammonia acts as a base in water, so we have NH3, and if it's acting as a base, that means it has to take in a hydrogen. So it's going to go from NH3 to NH4, and it's always taking in H+. So that's why we have the plus charge here. And of course, then where did that H come from? Well, it came from the water, so water gave away H, which makes it an acid. So now we're left with OH-. So if this was the base, then this is going to be the conjugate acid. And if this is the acid, then this is going to be the conjugate base, because it's always the opposite on the other side. So if we want to think about a conjugate base of NH4+, so a conjugate base means that the NH4+ is acting as an acid, because every acid has a conjugate base. So therefore, this is going to be NH3, because it's going to lose an H+, because that's what acids do. So this would be considered the conjugate base. If I wanted the conjugate base of H3PO4, once again, this means that this is an acid, H3PO4 is. So we're going to get rid of one of the hydrogens, and it's going to become H2PO4, and this is just a 1- on here. And if I want the conjugate acid of CO3 2-, that means that this is acting as a base, and bases accept hydrogen, so this is going to be HCO3, and that's just a 1- on that one. So if it's asking for a conjugate base, then you know whatever substance is given is an acid. If it's asking for a conjugate acid, the substance given is going to be a base, because they're always opposite. So if we added this to water, so CH3 and H3, and it's got a plus charge on it, then we have adding this to H2O. And so this is going to act as an acid, because it's not going to want to accept more H+, because substances typically want to be neutral. So that's going to want to give away a hydrogen, and that means the water is going to act as a base. And so because this is acting as an acid, it's going to give away a hydrogen. So it's going to be CH3 and H2, and now that plus is going to be gone. And then this is going to be H3O+. So the water is acting as a base because it's accepting a hydrogen, which means over here it's going to be the conjugate acid, and right here is our conjugate base. So if we look at B, B is negative, so it's going to want to take an H+, so this will be acting as a base, and this doesn't even have a hydrogen to give, so it has to act as a base, so it will also take a base. Then if we look at our reaction here, it's N2H4 becomes N2H5+. So therefore, this one accepted a hydrogen, so that means this is a base. This would be the acid. This would be the conjugate base, because this is, these two go together, so it's an acid conjugate base. And then this would be the conjugate acid, because these two right here go together. So you have to look to see what happened. Did it take a hydrogen? If it did, then it's a base. Or did it give away a hydrogen? If it did that, then it's an acid. So here we go from H2PO4 minus to H3PO4. So therefore it took a hydrogen. So that means this is a base, which means this is the conjugate acid. And then this one gave away a hydrogen. So that means this is the acid and this is the conjugate base. And then on the last one, amphoteric means it can act as an acid or a base. So if it's going to do that, of course, it has to have a hydrogen in it. It can't be amphoteric if it does not have a hydrogen. So if I wanted to write it as an acid, it would be giving away. So this would be acting as an acid, be giving away the hydrogen. So then it would become SO4 2 minus, and then we would form H3O plus. And if I wanted it to act as a base, it would be taking in the hydrogen. So therefore it would form H2SO4, and we would have OH minus. So amphoteric substances can act as an acid or base. Water is a perfect example of an amphoteric substance. Right here it's a base, right here it's an acid. But there are other substances that can be amphoteric. They have to have a hydrogen in them to be amphoteric.